Hi guys, and welcome back to the MLE GCP videos. This is video 2 of Unit 3, so overfitting, underfitting, and regularization. And I think it's really worth hammering home on these points. They do come up in the exam, and they're not that complicated, but they are a really easy way to get marks. They're quite tested, so I hope to fill you with confidence. Let's get going. So let's go through a bit of a recap first of training, testing, splits. So we covered this in Unit 2. This is talking about when you're feeding some data to a machine learning model, how do we split the data such that we have a bit of data for the test and the final evaluation, a bit of data which is acting like a mock, and some examples, which is the majority, right? So the training data here, that was the examples. So there you're giving the model the inputs and giving it the outputs, the sort of associated answer with those inputs, and you're teaching it. Just by saying, here's a worked example, knock your socks off, go read. And the validation set was a bit more like a mock test, right? So, or a homework, if you like. So you're giving the inputs and you're not giving the output, and you're saying, give it your best shot. And after it tries, then you give it the real answer and you say, okay, read your corrections and get better, right? So you're allowing it to learn from its corrections, the validation set. And then finally, the test set. This is where we evaluate the model's performance overall. So this is akin to the end of year exam that you might sit, and you only have one shot at this, and that's it. Once you get that, that is your final grade. That's how we evaluate our model. So that's how we need, this is what we need to optimize for, right? And we use the training and validation sets to judge how well we're getting before we use the test set, just like we use homework and work examples to help us get better. And by looking at the scores on those, we can determine if we're getting better before sitting our final end of year exam. Okay, so overfitting and underfitting, how does that play in? Well, overfitting and underfitting are related to the training on both the training and the validation sets. And overfitting might happen when there's too much training on the data that we're used to. So let's start with underfitting, actually. So underfitting happens on the other way around, when there's not enough training. Okay, so you might make some simple approximations to what you're learning, and you might get some general underlying concept, but you're missing a lot of it. Okay, so that's what this kind of straight linear relationship is looking like. It's kind of got something, but it's missed a lot of the steps along the way. It hasn't captured this curvy feature, and maybe well, in the long term, it's not going to be a good model. We can kind of predict that the model is going to go up here, and the data is going to go up here, and the model would look to go out this way. It's not really that accurate, and we could do better. Okay, so that's an example of training on the training set, and the validation set could be improved upon. Okay, and the test set, right? It's got some error in it. Right, and then the overfitting model is a bit on the other end of the spectrum. It's trying to fit to its data too much. It might be too complicated, it might be too complex. It also might be trying to make relationships between things that aren't there, just to make sure it works, right? So looking at every single example and over-analyzing. And it's generally very, very bad to have an overfit model. We don't like that. It doesn't generalize well to the model. That's to the real world. That's the key. Okay. So if we ask the overfit model, what's going to happen next on this chart, it might tell us, oh, of course, it comes all the way down here and then it goes up again and it goes even lower, or whatever. It's a bit on its own out there. It might miss the underlying trend that we see in the perfect model just by eye, that it's kind of got this trend to it, right? So that's what we're looking to mitigate. We're looking to mitigate this messy overfit model, but we're also trying to mitigate this underfit model. We would like something right in the middle with this perfect, really good model for generalization. So not just memorizing, which is this bit, and not just a simple generalization. We want a good approximation, right? Moving forward, good predictions, good generalization, which is this perfect model. Okay, so regularization. The first thing to say about regularization is that if you have an overfit model, regularization will help. And if you have an underfit model as well, it can also help a little bit, but it's mainly for overfit models. Okay, it's very common So before we talk about overfitting, we're going to have to talk about loss functions. But just on a really simple analogy, this is kind of what's going on. So we have some values, some predicted values, right? We see this very large line, and after some regularization, we're just getting it to calm down. We're getting it to get closer and closer to a simple model, okay? So we're getting it to reduce. That's the main premise, the main use case of regularization. So simplifying and getting it to be closer to the true answers. So reducing the errors. Right, so let's talk about loss functions again. Then we have to introduce them, saying as regularization does involve loss functions. So what we're looking at here, we've also taken from a previous video covering loss functions, and we're looking at the L2 norm and the L1 norm, so two different loss functions. And in blue, we have this mean squared error. It's rather lovely. We're very used to that. And in red, we have this L1 norm, okay, which is just exactly the same as taking your value and you're minusing away from the true value, and you just get this, you just get a measurement essentially. So you're just X far away, or whatever that means. And it doesn't matter if you're plus or minus, you're just X away, right? So with these two, we can tell some pretty key differences. So the first important difference is the L2 norm in blue shoots off to the sky very quickly. Okay, it doesn't take long before the L2 norm is shooting off up here in both directions, right? And the L1 norm doesn't. It gets trumped very quickly. If I've drawn this any good, it should be around 1 where it's better, but doesn't really matter about that. So L2 norm, it's very punishing. So it penalizes very strongly as a loss function. So that's similar to having a really, really strict teacher. As soon as you make any reasonable error, they point it out and they tell you very strictly, look, this is not good enough. And that's the L2 norm. Whereas the L1 norm, it'll tell you something, but it's not. It's a bit more relaxed, okay? And that they both have their pros and cons, but generally L1 norm, if you have that, if we're using that only, we could get some pretty serious overfitting alone with just that. So if we're very wrong, we really ought to fix that. That's the main takeaway, and we ought to use L2 norm, okay? If we're very wrong, we really want to know about it. So what we're doing with regularization, let's imagine these two as two different teachers, right? Let's imagine L1 norm is your nice, relaxed, lovely teacher who doesn't really mind if you get things wrong, but it's whatever. You're not going to learn too much from him in the long run, but it's quite relaxed, okay? And the L2 norm is your very strict teacher. If you get something wrong, as soon as it's a little bit more than acceptable, they're going to tell you, and they're going to tell you really strictly, okay? And it hurts in the short term, but in the long run, it's very helpful. So what we're doing with regularization is that we're using a combination, keyword combination, of two loss functions, or more than two loss functions. So what we might do is we might have, well, L1's our favorite, right? So we'll listen to that for 70% of our feedback. But the other 30% of our feedback we'll take from the strict teacher, right? So if the strict teacher says we should really, really, really do this, well, okay, we'll listen. We'll make some adjustments. But by and large, if we're a little bit off, if the L2 norm teacher is telling us, oh, this and that, whatever, we'll just listen to our favorite because we're not that far off. Okay, so that's what we're doing. We're going to take a combination of both the L2 norm and the L1 norm, or whatever loss functions we're using. And the purpose of that is that we'll be correcting for our most wrong errors. And if we can do that, then we'll be hopefully reducing our overfitting to more of a perfect model fit. But also under the underfitting model, we're helping it to adjust more carefully to the data. So here is a pretty big error, right? We're very far away from our values here. And we'd be telling it that is really wrong. Even the small, the 30% weighting or 40%, whatever you might choose in your model, the really strict teacher, the L2 norm, would have a lot to say about this bit. So it'd be very helpful. But then also for our validation set in this section, what's really going on is if it makes an error, just like if, as we earlier said, it might predict something like this, it would say, no, this is seriously wrong. That's a big error. And you'd see a lot of simplification change to make it a bit more perfect. Okay, so it's really not too scary. All we're doing is taking a combination of more than one loss function, and we do that to correct for a lot of the errors that might be inherent from just taking one loss function. Okay, and it's very, very good at reducing overfitting, but it's also helpful for reducing underfitting and creating this perfect model. Okay, good. I think we'll leave it there. That's overfitting, underfitting, and regularization. See you in the next one.